Once you've calculated the rate of reaction at a number of different urea concentrations like we did in Lab 9 for 1 millimolar, 2.5 millimolar, 5 millimolar, 10 millimolar, and 20 millimolar, then you'll be ready to calculate the Km and Vmax. To do this, to show you how to do this, I'm going to use the lab data from one lab section. This is what the various groups in one lab section data looks like. In most cases, the rate of reaction increases as urea concentration increases, as you can see here. The data is not always ideal. We do have some things where, for example, the rate of the reaction here increases for the first 3 urea concentrations, but then actually decreases. That's probably something went wrong there. Anyway, if we take an average of all of the lab's data, we'll get some value that's closer to the true value. So let's do that. Equals average, and we'll select all of the values for 1 millimolar urea. Say OK. Let's do a standard deviation of the same thing. Equals standard deviation, and say OK. We get a standard deviation and an average rate. In Excel, if we want to fill in all the other values for all the other urea concentrations, we don't have to do that calculation again. We can just do a fill down. And let's plot this to see how it looks. Plots actually allow your eye to really quickly see whether the data makes sense, easier than numbers, I think. Let's scroll down here a little bit. Okay, so we see that our rate of reaction increases as the urea concentration increases. Maybe I should put a axis labels on here. Oops. Axis titles. So this would be that's absorbance. That's minutes. Okay. And we could put error bars on this too to see, to capture how much error was within the lab group. We could do that by saying go to chart tools and add error bars, more error bar options. Come down here, click custom when you're on this tab here, and say specify value. Feed it all the standard deviations. Delete the one. Highlight the same standard deviations. Then we'll delete this horizontal error bar. It has no meaning. By just clicking backspace once you highlighted that. And you see that we have quite a bit of variation in our different our different rates. But because the error is most likely just random error between different groups, and there was nothing intentional, no lab group was trying to make the reaction rate really fast or really slow on purpose, the data cancels out. So a faster rate cancels, a rate that was too fast or abnormally fast cancels out with someone else's data where it was abnormally slow. We get a decent graph. Now anyway, once we have all of these averages, we can calculate, we can change absorbance per minute to millimoles per minute. To do that, we have to use Beer's law. And so we know that absorbance equals the extinction coefficient times the path length times the concentration. So we can rewrite that to concentration equals absorbance divided by the path length and extinction times the extinction coefficient. Anyway, let's just show you what the math would look like here. So it will say equals absorbance, or in this case it's going to be absorbance per minute. So we're going to get not millimoles, we're going to get millimoles per minute, divided by the extinction coefficient, which is 0.07 in this case, and the path length is 1.3 centimeters. So if we did that, we change absorbance into millimoles per minute. But we're not actually really finished that. So we have one more thing we have to do. We have to figure in our dilutions, right? So we did a 1:3 dilution. I'm going to just make this clear. I'm going to put a parenthesis around that equation. We did a 1:3 dilution where we took only 100 microliters of your 300 microliter stock. So we'll multiply that by 3. And we also we had a total reaction volume of 1.1 milliliters, and we only took out 0.2 milliliters at every time point. So we have 11 halves dilution. So 11 halves. So these will be our two dilutions. They equal 16 and a half total. So now we have our corrected millimoles per minute. That's the millimoles per minute that was in your reaction test tube. Not absorbent, no longer the absorbance that you had in your detection tube. We'll do a fill down also on that. And now we're almost there. We're almost where we can calculate the Vm and Kmax. To calculate Vm and Kmax, we just have to do a Lineweaver-Burk plot, or otherwise known as a double reciprocal plot, where we're going to take 1 over the urea concentration, the substrate concentration. So we're going to say equals 1 divided by, you look here, that urea concentration. So we're going to have that equation right there. Say OK. And we'll also take 1 over equals 1 over the rate of the reaction, which is this cell here. Right, so 1 over the millimoles per minute. So here's our equation. Enter that. And then we do a fill down. And we get these numbers here. Right. And so now we need to make a Lineweaver-Burk plot out of that data. So we'll graph this again. We'll highlight these guys here. In the lab, of course, for the lab practical, you're going to have to do all of this by hand, but the math is going to be the same. So you should be taking good notes, and you should be really ready to go to make all of these very simple calculations. You know, just 1 over the rate, 1 over the substrate concentration. Insert chart. We'll pick a scatter plot once again. And you can see that we got points that are roughly in a straight line. So this lab section, the average of what this lab section did looks good. We were expecting to see a straight line. If we click this here, we can add a trend line now. Right click on one of these points at this point, or hit or press Control click on a Mac, but on a PC it's a right click, add trend line. We'll have a linear, and what we want this line to be extended to the x-axis, right? So what we're really after in this Lineweaver-Burk plot are the y-intercept and the x-intercept. So we'll say forecast backwards. Let's put 0.5, and the line extends. And then this is what you guys will have to graph. You have to make a graph that looks like this in the lab section or in your lab practical. You can label. Let's label this guy up. Add chart elements, axis titles, horizontal. So this will be the substrate concentration, or 1 over it. So we'll say millimoles of urea, and we'll this whole thing to the -1. If we want to make that look better, we'll highlight this. Sometimes it's hard to highlight just that. And then go to Home and click here where it says Font. And then you're going to say Superscript. Okay. And we have the y-axis would be the 1 over the rate. So we'll insert an axis title for that one too. Say call it millimoles. Millimole per minute. Put that in parentheses. Right to the -1. Highlight. If you can do it. Highlight just that. Make it a superscript. Okay. So now we have millimoles. I guess this would actually, we should change this. Let's make this even more accurate. Millimoles. Millimoles ammonium. I'm trying to make it longer, but it's not letting me. Anyway, good enough. So finally, if we go back to our trend line, if we want to use Excel, use the power of Excel to calculate the Km and Vmax, we can use that equation of the line to solve for these intercepts. To solve for the y-intercept is really simple, right? So we're going to put 0 in for x. So let's do that. If we put 0 in for x, the 1 over the Vmax would equal just basically 1.5461. Right. So if you're doing this with graph paper, you're just going to estimate where exactly that's crossing. The bigger you make this graph, the easier it's going to be to get a precise y-intercept manually. All right. Alright, the x-intercept is equal to 1 over the k, negative 1 over the km. So this x-intercept here is equal to minus 1 over the km. As we can see, this value is about negative 0.4. If you were doing this in the lab practical, you would just put minus 0.4 for that intercept. If we would like to use this equation to get a really ultra precise value of that x-intercept, we could solve for x in this equation here. So we'll put 0 in for y, and we'll solve for x. So if we put 0 in for y, the first thing we want to do is we want to move this guy to the other side. So we'll subtract both sides of this equation by minus 1.5461. So say equals minus 1.5461 minus. And then if we want to solve for x further, we need to get rid of the 3.8989. So we'll divide both sides of the equation by 3.8989. So anyway, this equation right here solves for x. And you see we get almost exactly the same thing. So that x-intercept was negative 0.39655. That's almost the same thing we predicted manually, right? Of course, we don't want negative a 1 over Vmax and a negative 1 over Km. We want the actual Vmax and the Km, and that's of course really simple to calculate. Vmax, Kn, and we're just going to take the inverse of each one of these numbers. So we'll divide that. We'll do 1 over that number. That's the equation right there, 1 over that number. And that's our Vmax. The units of Vmax are the rate of the reaction, so it's the maximum rate that the reaction can go, and so that's millimoles ammonium per minute. Okay. Km is the same thing. We're going to take the negative, we're going to take the inverse of it. We're going to do minus 1, divide that number there. So we're just basically inverting this and taking the negative of the inverse. And so there's our Km. Our Km is the concentration of urea where the reaction rate is half its maximal rate. It has units also, so it's millimolar urea. All right. So now you've done a whole lot of things in this lab to finally calculate a Km and a Vmax, and that's a lot of what scientists do. They do a lot of complicated. They take a lot of complicated things and they make them simple so that they can be simple and explainable to other people, other scientists.